Imagine Earth suspended in the black silence of space, a delicate sphere of oceans, forests, and breathable air. It may seem serene from afar, but this oasis is under constant siege. Every second, our planet is bombarded by high-energy particles. Streams of charged solar wind burst from the sun's surface, racing across the solar system at supersonic speeds. Occasionally, more violent eruptions, solar flares, and coronal mass ejections hurl billions of tons of plasma toward Earth, capable of disrupting technology, scrambling communications, or worse. Beyond our solar system, the universe sends its own barrage, cosmic rays, subatomic bullets from dying stars, and galactic explosions. Left unchecked, these would wreak havoc on any life and technology within their reach. Yet, despite this relentless assault, life not only survives on Earth, it thrives. We owe this miracle, in part, to an invisible, unheralded barrier, the Van Allen radiation belts. They are Earth's unseen armor, high above the clouds, holding back space's fury with an elegant, electromagnetic grip. For centuries, the space surrounding Earth was a mystery. Scientists suspected Earth's magnetic field extended into space, but they had no way to test it until the dawn of the space age. In 1958, at the height of the Cold War and the birth of the space race, the United States launched Explorer 1, its first successful satellite. Its payload was modest, a Geiger counter designed by University of Iowa physicist Dr. James Van Allen to measure cosmic radiation beyond Earth's atmosphere. What Explorer 1 recorded shocked the scientific community. Rather than a steady stream of radiation, the detector found two belts of intense, concentrated energy, so strong they maxed out the Geiger counter, a phenomenon known as instrument saturation. Later missions confirmed the discovery. These belts, looping in donut-shaped rings around Earth, were named in honor of their discoverer, the Van Allen belts. It was the first major scientific revelation from space, proving that Earth's magnetic field doesn't just deflect solar particles. It traps them, holds them, and shapes them into a protective cage. The Van Allen belts are composed of energetic charged particles, primarily electrons and protons, captured by Earth's magnetosphere, the magnetic field generated by the movement of molten iron in the planet's outer core. There are two primary belts. The inner belt, stretching from about 1,000 to 12,000 kilometers above the Earth's surface, is densely packed with high-energy protons. These particles can persist for years, creating an intense radiation environment. The outer belt, from roughly 13,000 to 60,000 kilometers in altitude, is dominated by electrons moving at near light speed. This belt is more volatile, fluctuating in size and intensity in response to solar activity. But the structure of the belts is not always so neat. In 2013, NASA's Van Allen probes discovered that during intense solar storms, a third, temporary radiation belt can form, an unexpected layer, proving that the system is more dynamic and mysterious than previously imagined. These belts are shaped not just by Earth's magnetic field, but by the solar wind's constant pressure and the electric currents it induces. They are a dance between star and planet, a magnetic ballet unfolding in the vacuum of space. The Van Allen belts are part of a larger, more powerful structure, Earth's magnetosphere, an immense, teardrop-shaped magnetic bubble that stretches nearly 10 Earth radii toward the Sun and extends far beyond the Moon on the night side. As the solar wind approaches Earth, it slams into this magnetic field, compressing it on the sunward side and elongating it into a long tail on the dark side. The magnetosphere bends and flexes like a living organism, absorbing and redirecting energy. Inside this shield, the Van Allen belts act as internal holding zones, capturing high-energy particles that manage to slip past the outer defenses. Without this dual-layer system, the full force of space weather would descend upon our atmosphere and surface unimpeded. And when the sun lashes out with its most violent eruptions, solar flares, and coronal mass ejections, this magnetic system is put to the test. It flares, it shakes, but it holds. When a solar storm hits Earth's magnetosphere, a surge of particles floods toward the planet. Some are deflected, others trapped in the radiation belts. These particles spiral along magnetic field lines, ricocheting between the north and south poles at near-light speeds. This dance of electrons and protons creates more than radiation. It powers the auroras. Brilliant greens, purples, and reds shimmer in the polar skies, visible signs of invisible forces. Though auroras occur below the Van Allen belts, they're connected. Both are driven by solar energy and Earth's magnetic response. But there's a darker side. Intense solar storms can pump the belts full of energy, making them hazardous to satellites and astronauts. Radiation levels can spike by thousands of % in hours. And yet, the belts contain these dangers. Like pressure valves, they store and slowly bleed off energy, preventing catastrophic surges from reaching our surface. They are not just barriers, they are regulators, managing the flow of energy from the cosmos with exquisite precision. As humanity pushes deeper into space, the Van Allen belts become a critical concern. For satellites, especially those in high orbits like GPS and communications satellites, radiation from the belts can cause bit flips in data, degrade solar panels, or even destroy sensitive electronics. Engineers now build radiation-hardened systems and shield spacecraft to endure prolonged exposure. Manned space missions must plan routes carefully. During the Apollo missions, NASA designed flight paths that minimize time within the belts, limiting astronaut exposure to acceptable levels. Future missions to Mars or deep space will require even greater understanding and protection. The International Space Station orbits far below the belts, safely tucked inside Earth's magnetic field. But as we dream of lunar bases and interplanetary travel, we must learn to navigate and respect the volatile zones above us. Understanding the belts is not just a matter of curiosity, it is a matter of survival. The Van Allen belts are not static. They breathe, they pulse, they shift and respond to the moods of the sun. Their structure changes with solar cycles, which rise and fall over an 11-year rhythm. Their energy swells during periods of high solar activity, then quiets during the solar minimum. They respond to magnetic substorms, sudden reconfigurations of the magnetosphere that release vast amounts of energy. During these events, the belts can expand, intensify, or even collapse temporarily before rebuilding themselves layer by layer. Through missions like NASA's Van Allen probes, Themis, and Cluster, we've learned more in the past 2 decades than in all the time since their discovery. But many mysteries remain. How exactly do particles enter the belts? What causes some storms to supercharge them, while others leave them untouched? Each new discovery brings us closer to mastering this magnetic shield and to better preparing for life beyond it. High above our skies, unseen and uncelebrated, the Van Allen belts swirl in silence. They do not shine like stars, nor move like satellites. Yet they are among the most important features of our planet's space environment. They protect us from the sun's wrath and the galaxy's fury. They regulate the flow of cosmic radiation. They allow our atmosphere to endure our technology to function, and our species to survive.